Okay, so we have our memes of the week. Because it's cold outside, I thought that this little cat was relevant. 6-year-old me blowing air out of my mouth to feel like a dragon. I don't know about you guys, I actually still do this. Yeah, there was a 90s movie called Cool Runnings. I don't know if anyone ever watched that, but there's this guy, it's like, bro, why you smoking? And the guy's like, I'm not smoking, I'm breathing. It's one of my favorite lines. Anyways, none of you care about that. Um, and then I've got this one. Eels are fun because they always look like they just told you a joke and are waiting for you to laugh. That's my hubby. He actually posted that. I thought it was great, so I decided to share it. Okay. And
This is
last one.
Facebook.
What was that, Joseph?
Is this on Facebook?
I don't know. Probably looks like it might have been.
That's awesome.
And this is the last one. Crazy how beavers just see running water and just think to themselves, well, someone has to put a stop to this. It kind of makes sense though. Why do animals do what they do? We'll never know. Alrighty. So we're back. Yay. We're starting chapter 7 from the text. So that's fundamentals of statistical inference. And we kind of mentioned statistical inference, I think, in the first lecture. That was several weeks ago now. But hopefully everybody was able to look at their feedback from the exam. Um, Overall, like, you actually did a really good job. So I would actually venture to say that you guys probably had the best performance on a first exam that I've ever had in a class before, or like in this class specifically. So really, bravo, well done to you. Um, but all of those are posted. If you have questions or haven't reviewed your exam yet, just go ahead and check it out, see if it works. If it doesn't, let me know. I haven't heard from anybody about it not working yet, so I think we are good to go. But today's lecture is going to be kind of important for setting up the rest of the semester. So concepts that we introduced today, there's kind of a lot to remember, but it's going to the concepts in this lecture just going to be repeated pretty much every single week from here on out. The only difference between weeks is that we're just looking at all of this fundamental knowledge in different statistical tests. Okay, so the context is going to change, but the actual concepts are going to pretty much be the same. So we're going to talk about what statistical inference is. I've given you guys a definition before, but it's always good to revisit. We're going to talk about sampling error, which we've actually touched on just a little bit. I think I want to say 2 weeks ago, maybe. It's when we talked about standard error. So that's one type of sampling error we can look at. But anyways, we're also going to go back to hypothesis testing. So again, we kind of had an introduction to this in the first week of classes, but now we're going to dive in. Sometimes you guys have heard me say like, oh, this is a two-tailed hypothesis or a one-tailed hypothesis or a directional hypothesis or non-directional. So we're going to break hypotheses down a little bit further and then start to look at how different statistical tests might read the hypotheses and how you would actually lay those hypotheses on a distribution. If you are a visual learner and you like that visualization, today should help kind of conceptualize that component we're going to go over today. Once we talk about hypothesis testing, we're going to get into confidence intervals, and then we'll also talk about types of error. So again, all of this ties into the larger topic of statistical inference. So we're gonna introduce that while also talking about sampling error to start us off. Okay. So some stuff that we've talked about before. What are things to consider when we collect samples? What kind of characteristics ideally should our samples have? Someone put in the chat. They need to be random, absolutely. Okay. What else? Normally distributed, yeah, Morgan, absolutely.
Don't you want to account for like human error?
Mm-hmm. Yeah.
Maybe you should have inclusion and exclusion factors for your sample.
Mm-hmm. Right. Samples need to meet certain inclusion exclusion criteria. And Tiffany, I'm glad you said that. Yeah, Z, same thing. Controlling for internal validity when we're measuring to make sure that our sample, all of this is getting to one concept, that our sample is representative of our population, right? So it needs to be random, and then it needs to be representative of a certain population, which that population is specified using our like inclusion exclusion criteria, right? So we can make the population, theoretical population, as specific as we want it to be, or we can make it more generalized, right? And that was one of the trade-offs we talk about. If you are trying to increase the amount of internal validity, right, which means it's a good thing. The more controlled your study is, typically, the more specific your population is going to be. However, a whole part of statistics is that we're also controlling for external validity and boosting that as well, right? Which is our generalizability to the population. So I think in the first week we kind of mentioned there's a trade-off. If you're increasing internal validity, you kind of end up decreasing external validity. But the goal is to find a balance. And that all draws back to statistical inference, right? So we collect samples because we need some subset of the population so that we can test that sample, right? And then infer certain characteristics about that sample onto a given population, okay? So it's all about generalizability. How does your small subset of the population indicate what you might expect to see in the entire population, right? Usually we can't collect the population, so samples are really important. And that's all that statistics is about, right? So like in kinesiology, we could have people undergoing certain fitness interventions, right? To see how those fitness interventions affect certain health outcomes, right? We could have a control group, we have an experimental group, okay? And each of those groups is representing the population of interest, right? That's kind of narrowed down by our inclusion exclusion criteria. So the control group, we like to say, is from the population. They are representative of what the population would be without an intervention, right? And then basically with this statistical inference, we can say if the experimental sample has boosted health outcomes as a result of this intervention, their fitness intervention that we give them, then that experimental group is statistically significant enough, right, or different enough from our control group that we consider both of them from different populations, right? We've identified if those certain characteristics separate these two groups, that they are representative of different subsets, right? So that's one example of things. If we're looking at effects of interventions, we can also look at correlations, which we'll talk about next week. Okay, but everything is coming back to how does the sample relate to the population? Okay, just want to drill that in there. Excuse me. But when we talk about statistical inference, we have to talk about sampling error. And we've kind of commented on or introduced this topic before. But what sampling error is it's how much error you have in the estimate of your population parameter based on a sample statistic, right? So we've talked about degrees of freedom. You know, we had like the variance equations and there was an n-1 at the bottom. Part of that kind of helps with the sampling error, right? Because we said, oh, you add degrees of freedom because you never have everybody in your population. So in a way, we overestimate the variability with those degrees of freedom for those variance equations, okay, or variability equations. So sampling error is more or less another way to do what we did previously. Okay, and we've mentioned this in terms of standard error so far. Okay, so I'm gonna shift slides so we've got a visual representation of stuff soon here. Okay, but it's just basically the standard error is like a standard deviation for a population. Okay, I'll say that again. Standard error is kind of like a standard deviation for a population. So when we think about standard deviation, that's indicating some deviation from the mean or some distance from the mean for a certain raw score in a sample, right? Standard error is translated fairly similarly, except instead of looking at a raw score in a sample, we're looking at a sample mean within the population. Okay, so the standard error of the mean is saying how far away from the mean of the population, which is estimated, right? How far away from that estimated mean is a given sample mean? Okay, so the formula that we use to figure out this standard error of the mean is a sample's standard deviation divided by the square root of the sample size. Z asked a question, would this have a rule like the empirical rule? I think I understand what you're saying. And kind of, yes. We never really use the standard error to assess, like we don't use it directly to assess like distance from a sample from a population mean. However, the standard error of the mean is incorporated into a lot of equations that will give us values that tell us if we're close to that empirical rule area, which is what we're going to get into today. So I'm kind of glad you're thinking ahead already. Okay. But this standard error, again, distance from the estimated population mean, right, is telling us where is a sample mean somewhere in relation to that population mean. So when we're collecting samples, it's important, right, that we pay attention to these two variables, okay? Standard deviation is a variability measure, right? So if you look at the relationship between standard deviation and standard error in the equation, they're directly related, right? So as variability of the sample increases, so does the standard error, okay? Greater standard error means that our estimate of where our sample is in comparison to the mean, it's just getting bigger, right? So you can think about it as standard error as variability measure for the population as well, okay? So we wanna make sure that our standard deviation is fairly low for our sample. Okay, that way we understand that the spread of data isn't so wide that we're kind of, or potentially including people that aren't supposed to be in that sample. Okay. The other thing we want to control for is the sample size. So you can see sample size is indirectly related to standard error. So that means the lower your sample size is, the higher the error, right? And we want to make sure that standard error stays low so that our estimate is more accurate. Okay, so increasing sample size, that's one of the other reasons why we want a good sample size, okay, other than decreasing the variability in the sample. But let's put this into a visual representation, okay? So these are arbitrary numbers on this axis, okay? And for the sake of this example, I liked the way that this photo was plotted, but just pretend that instead of X bar, this is a mu or a population mean. Okay, so each of these plus signs on this distribution are going to represent a sample mean, right? So when we take, you kind of think like we just keep blowing up this pattern. So a sample is a bunch of individuals, right? And then we put all of those individuals and we get a mean. So that would be a sample mean, which was one of those little plus signs on that distribution. Okay. If we take a whole bunch of sample means, basically a ton of different samples, right, and we plotted them in a distribution, we kind of get an idea of what the population shape would look like, or what the population distribution would look like. Okay, so again, all of this is statistical inference. How does the sample fit into the population? Okay, and there's butter. Okay, maybe not right now. Okay. Where was I? Yes. Okay. So again, this is our estimated population mean. Okay. We'll just say it's in the center and it's beautiful. Here we go. Okay. So now we're going to kind of get into the introduction for levels of confidence, and that'll lead us into confidence intervals, but I like to introduce them step by step. So we have an estimated population mean somewhere in this distribution. Okay. You will have a level of confidence that you identify. Okay. So basically this more or less, we'll have some examples, but usually it's anywhere between 90 and 99. Okay. And it is what it sounds like. So the level of confidence is kind of the area where it's the greatest likelihood, or has the greatest probability of what the population would actually consist of. Okay, so you can think about this area, right, where we've said like 95% level of confidence goes with a 0.05 alpha. We've mentioned that once before. But if you guys have seen literature and you're like, oh, we used a p-value of 0.05 as our marker of significance, right? 0.05 is just telling you that like 5% chance of error would be accepted, but we're 95% confident that we have gotten the results that we have because of the effect that was observed. Okay, so the level of confidence is generally just saying, where do we expect most of the population to exist, given the sample statistics that we were able to calculate. Okay. The other areas, right, that aren't included in that level of confidence are where your alpha is. Okay. And alpha is just going to be like if you have your level of confidence and this is 100% of the sample, right? You're 95% confident that a majority of your sample will lie in this region, but you have an additional 5% made up of alpha, okay? And alpha can be above the mean, it can be below the mean, it can be on both sides of the mean. It kind of just depends on the type of test you have, and that's what's gonna transition us into our hypothesis testing, okay? But alpha we can also call the region of rejection, and we'll get into some examples of why we call it that in a little bit. Okay. Does anyone have any questions so far?
Did you say region of rejection or projection?
Rejection.
Okay, thank you.
Mm-hmm. We could put this into words too, might help a little bit. It's our level of confidence is the percentage, right? That establishes that the null hypothesis is true. Okay, so it's basically saying, where do we think a majority of the population would lie, right? Such that there is no difference, there is no relationship. Okay, and then the opposite of that is our alpha, which we often call a probability of error. It is actually a certain type of error, but we'll get to that in a little bit. Okay, and P, we could refer to probability as P, okay, and that'll be consistent for the rest of this semester. Most times P will be equal to alpha, and that's going to identify what your criteria is that you're judging calculated p-values on in your statistical tests. Okay, so usually if we say that our level of confidence is 95, okay, we can figure that out by saying 1 minus whatever our acceptable probability of error would be and multiply it by 100 so that it's represented as a percentage. We can flip that equation and just say 100 minus the level of confidence, or 1 minus the level of confidence written as a decimal. So in this case, 1 minus 0.95 would be 0.05. So level of confidence and probability of error are mutually exclusive to each other. Okay. But usually we represent P or alpha, right, as the probability that you were wrong because of error. So we always want to keep some degree of error available because we don't know if we've made a sampling error. We don't know if we've made investigator error, or if there's been bias that's been included by certain individuals. Could be the actual investigators, it could be instrument bias, it could be participants, okay? So it's just, there's always going to be some degree of error, but we set alpha at a level that we're kind of willing to accept, okay? The other way we can look at P is the probability that the null hypothesis is incorrect, right? Which is, or is correct. I guess you could kind of phrase it either way. Maybe the null hypothesis, or P is equal to the probability that the null hypothesis is correct, in the sense that, well, I'll get to this in hypothesis testing because I don't have visuals, so I think I'm just gonna confusing you. I didn't say anything, I'm just gonna keep talking. Okay, sorry. So when we put level of confidence and our alpha together, right, they're gonna be mutually exclusive, so it's out of 100 or out of 1 if you're looking in decimal format. But the primary examples that we usually have in research are 90% meshed with a alpha level of 0.1, 95% meshed with an alpha level of 0.05, 99% with an alpha level of 0.01. Okay. So with that, we're going to go into hypothesis testing, and then some of the things that I just said that I should not have said yet will probably make sense. Okay, so this should look familiar. Okay, research hypothesis and null hypothesis. Does anybody want to say which one of these is statistically tested?
The null.
The null. Right, that was a test question. So the null hypothesis is always tested because we always have to assume that innocent until proven guilty concept, right? There is no effector relationship until we prove that there is one. Okay, so the research hypothesis is always going to be what your predicted outcome will be. The null hypothesis is the opposite of whatever that predicted outcome is. Okay, so we can have two different options. The first is that we can have a non-directional hypothesis, which means that the research, or if you're trying to argue that there is a difference between two groups, so I'm using mean 1 and mean 2 as examples here. The null hypothesis you're arguing says that those two groups are different. Their means are different enough that they're considered separate, or considered from separate populations. The null is mutually exclusive to that. So if this is, there is a difference, we don't specify what direction, but there just is a difference, okay? The null would say that those two means are going to be equal to each other, okay? So in this case, there would be no effect. The research hypothesis would be arguing that there is an effect. And like I said, we kind of call this non-directional because mean 1 could be greater than mean 2, but mean 1 could also be less than mean 2, right? So typically we use non-directional hypotheses when we're not entirely sure of what the outcome might be. If we have sufficient literature that's already developed certain relationships that kind of point towards an educated guess on what effect you might think you would observe, then we might use a directional hypothesis, right? So in this case, if your predicted outcome is that mean 1 will be greater than mean 2, okay, then your null hypothesis is mutually exclusive to that, and mean 1 would be less than or equal to mean 2. Okay. For this class, we most always use non-directional hypotheses because SPSS's default is two-tailed tests, which we'll talk about next. But two-tailed tests use non-directional hypotheses. Directional hypotheses we don't mess with, and that is one thing that I kind of notice students like to jump into in activities, is if I ask you like, oh, what is the like null hypothesis, or what is the research hypothesis for a given scenario? I always want a non-directional hypothesis. Okay, some students will be like, oh, we expect their flexibility to be greater than the control group because they had a flexibility intervention. Okay, we just say the groups are different from each other or they're not different. Okay, depending on which hypothesis I'm asking. So always use a non-directional hypothesis in this class. Okay, and I mentioned non-directional hypotheses use a two-tailed test, which is what SPSS will default to in our class. So with the two-tailed tests, we call it two tails because we are considering a region of rejection both above the mean and below the mean. Right, so you can think about alpha level usually has a very small probability or small percentage, and that's where the tails are of the distribution. Okay, so two-tailed test, that's where we get the name. When we have a two-tailed test, right, our level of confidence is set at the beginning of our research project. So let's say I wanted to use a 95% level of confidence, right? Based on 100 minus 95, that means my region of rejection should be a total of 5%, right, or 0.05. So the total area of alpha, both above and below the mean, should have a sum of 0.05, which is why we note it as alpha divided by 2. So each of these regions would be 0.025, which sums up to an entire error of 0.05. Okay. So typically, again, we're going to use a two-tailed test when we want to know the relationship or an effect of an intervention. Okay, relationship between variables or an effect that can't be majorly supported by literature. Okay, so established relationships don't exist yet to give us enough of ground to stand on to kind of make an assumption that we would expect a one-directional or a directional hypothesis for a one-tailed test. Okay, so this is the other example that we'll use. Right, so we said non-directional hypothesis specifies a direction, which means that our tail probability, alpha, is going to be on one side of the mean or the other. Okay, so I might argue that my sample mean is greater than my population mean. Okay, maybe that's what I'm comparing. And so if that's the case, right, my sample mean needs to land somewhere in this region of rejection in order for me to say that it's different from the rest of the population. Okay, we'll go through more examples of this, but alpha could be on one side, alpha could be on the other side. But either way, the region of rejection is always mutually exclusive to the level of confidence. So in this example, if we had a 95% level of confidence, right, the entire alpha area is going to be 0.05. And again, we're going to use one-tailed tests when we have an established relationship or effect that's already been consistently shown in the literature. Okay, but last time, just because I always get at least one person who thinks that we do directional hypotheses in this class. It's good to know both of these types of hypothesis testing exist, right? But again, our class, we only use non-directional hypotheses, which are related to two-tailed tests, where the sum of alpha is in one tail above the mean and one tail below the mean. Okay. So how do p-values work into this then? Right? We've kind of commented on when to accept or reject the null. Okay. But I like to again say that the p-value is the probability that the null hypothesis is true. You can also phrase it, the p-value is the probability that you have made an error. Okay. Either one makes sense. But the calculated p-value, okay, so when we run tests, I think this will start probably making more sense next week when you actually have values to work with. But every time you run a statistical test, you'll get a calculated p-value out of SPSS. You evaluate that value compared to whatever your set alpha is. So if alpha is 0.05, we compare some calculated p-value to 0.05. If we see that that calculated p-value is greater than the alpha level we set, that means we have a high probability that a type 1 error was made. Okay. So if think alpha is 0.05, that means we're willing to accept a 5% chance of error. Okay, so if our calculated p-value for a statistical test was 0.10, that means there's a 10% chance that we made an error, right? The greater percent chance that we made an error is, the more we don't want to accept our results, right? And not saying that our results are bad, it's just meaning we're not going to accept the predicted outcome that we said we would have, okay? So that's why you can also look at the p-value as the probability that the null hypothesis is true, because the higher this p-value is, the more and more you should say, I should accept the null. Okay, so I like to phrase that way as well. Okay, so when p-value is greater than alpha, we accept the null. If the p-value is less than alpha, again, we can look at this in two different ways. Either if your alpha is 0.05, you say, I accept a 5% chance of error, and that's it, right? Anything greater than that, we'll just say there is no difference between the groups or there's no relationship. But anything less than that indicates that we potentially have a difference, right? So there was a low chance that we made an error, or we could also look at it and say there's a low chance that the null hypothesis is true. Okay, so in either one of those cases, if you made a small degree of error, or you think that the probability that the null is true is really low, then we would reject the null hypothesis and go with our research hypothesis. Okay, and when the p-value is less than alpha, that's when we claim statistical significance. Okay, does anyone have any questions on this? Cool. We're gonna have some more examples and like figures to look at. But before we get into that, we're gonna talk about confidence intervals. Okay, so the confidence interval is basically just representing an interval or range around which the population something truly exists. I say something because we can look at confidence intervals for a lot of different things. And I think for our class, we will do 3 examples of confidence intervals. So that's why I kind of keep it open. But we could say a confidence interval is for a true population mean, right? So from our sample data, we can say within a given population, the true population mean, right, should exist between these two values. We could also do this for relationships. We can do it for mean differences between groups, which we'll get into when we start talking about t-tests and ANOVAs, right? There's other types of confidence intervals that we don't cover in this class, but all of them are saying basically what is the estimated range of the population parameter based on the sample statistic. And there is an equation that we use to calculate confidence intervals. It's going to change based on what you're calculating the confidence interval for. So we're going to start with a simple translation of a sample to a population, and that's just how do we estimate the population mean, okay? So this equation right here is saying what is it's going to give us the confidence interval for a true population mean compared to given sample statistics or characteristics, okay? So this is going to say that our confidence interval for our population mean is equal to the sample mean, x bar, plus or minus a z-score times the standard error of the mean. Whoa, we're starting to add in a lot of extra equations now, right? So the z-score is going to be related to the level of confidence that you set, which will be nice because this z-score is going to end up being constant for a lot of different examples that we can use. So it's not a z-score based on a raw score, which is the calculation that we've had previously, but rather it's in relation to certain probabilities under the curve for a given confidence level, okay? And we'll go over an example of this. So I have a level of confidence of 95%, and that 95% level of confidence is going to be associated with z-scores at plus or minus 1.96. Now these are the z-scores for a non-directional hypothesis or a two-tailed test, okay, just to make note. And then the confidence interval that I get is usually going to be noted in square brackets, where we have a lower bound, which is going to be the minus side, and then all the way up to the upper bound, which is the plus side of the equation. Okay, so if we put numbers into this, okay, I can say my population of interest is the age of individuals that live in mobile home parks. And I've collected a sample of 50 people. That sample mean age is 60 years old, with some variation of about plus or minus 5 years, okay? And we're gonna assume that this is normally distributed because we are using z-scores, and we're also using standard error. So again, both of those two things assume we have a normal distribution, right, if we're inferring sample onto population. So just tag that note there, okay? So if we use this equation to find the lower and upper bound of our interval, we would use a z-score of plus or minus 1.96, and I'll kind of talk about how we get that value. But basically we would say our sample mean is 50. Lower bound would be minus the z-score times the standard error, which we calculate by doing standard deviation divided by the square root of the sample size. So if I did that, I would get a value. And then if I did the upper bound doing plus, right, this factor over here, I would end up getting a confidence interval that looks like this, okay? So the confidence interval is going to be in the units of the thing that you're measuring, right? So in this case, we were measuring age. So we would say that the true population mean, right, for individuals that live in a mobile home park, we would say the estimated population mean would be somewhere between 58.61 years old and 61.39 years old. Okay. Any questions on that? Or like how we interpret the confidence interval? Cool. So we're going to do some examples. So if you have on Beachboard, I posted like a confidence interval sample calculation file. Go ahead and open that. And basically what we're going to do, we have our equations, standard error of the mean, which we know goes into our confidence interval equation. And then we're going to be calculating the confidence interval for some population mean, given certain characteristics about our sample. So I've given 4 different scenarios, and I'm going to segue into talking about how we get this information, but I just wanted to point out these are different levels of confidence that we can have. Again, 90, 95, and 99 are the most common ones, 95 being the absolute most common that we'll see. So when we have a level of confidence given here, we know we can say 1 minus the decimal version, right, or 100 minus the percent version will give us what this should be alpha, not p, right? But that'll tell us what our alpha level is, which is what we use to evaluate p, okay? And if we wanted to translate these boundaries into values based on our sample, right, we can use z-scores to say, well, 1.65 z-scores away from the mean would be some raw score, right? Because we know z-scores before that we've calculated incorporate some raw score minus the sample mean divided by the standard deviation, okay? So these are going to be helpful in kind of translating our confidence interval into actual units for what we're measuring. So I'm going to stop sharing really quick, and hello, there we go. We're going to go into, I can't minimize. Oh, it's because I stopped sharing, that's why. Duh, okay. We're fine. It's been a long day. Okay. So I want to talk about z-scores really quick. And that is now one thing that I realized I forgot to pull up. So give me 1 second. And if you have a z-score table, you can pull it up too. Okay, so this should look familiar, right? When we have a confidence interval, for our purposes, we usually say that we're going to use a two-tailed test, which means that we're going to have 2 areas of alpha, right? So alpha needs to be divided by 2. Okay, so we get half on each side of the mean. So if we say that our alpha level is 0.05, that means the area under each tail is going to be 0.025. Okay, so you can also say it as a total of 5% error with a 2.5% chance of error above the mean and a 2.5% chance of error below the mean. Okay, I think it's easiest to think about the percentage below the mean just because that's the area to the left that we're interested in, right, when we look at z-scores. So if we expect to have a 2.5% chance of error or a 0.025 chance of error, we can look that probability up in the table, right? So I can scan these values in here and say what is the closest thing that I can find to 0.025. So I'm kind of coming up to this part, and look, I actually found 2.5% chance of error, 0.025 probability of error, right? And that lines up at negative 1.96. What? That's the value that I gave you guys, right? 1.96. And we can just say it's plus or minus 1.96 because, again, that probability exists above the mean as well as below the mean. Okay? But that's how we get our values. So if we had a level of confidence of 90%, that means we have a 10% chance of error that we're willing to accept. If we have a two-tailed test, we would say 10 divided by 2 is equal to the area under each tail, which would be 5% or 0.05. Right? If we looked up 0.05 in our z probabilities, we get to kind of between these two values, okay? And this is another thing that I want to comment on, is that you always want to overestimate your error instead of underestimating your error. So if we're willing to accept 5% chance error, we're not willing to accept any less than that. Otherwise, it's like we're compromising our morals in terms of what we deem statistically significant. Okay, so you always want to overestimate your error, meaning the probability or the area under the curve should be higher than what you're anticipating if you kind of get stuck in this situation. So for this one, we would say we have 1.64 or 1. Oh, actually, no, it should be 1.65. So you want to, I think I said that backwards. Ah, damn. Okay. This is an example. I always get these two confused because there's another example that we talk about, and I don't think it's this week, but it's in a coming week when we talk about power, and I always get these two messed up. Okay, my bad. You don't want, you do, it's okay to overestimate error. So, because you don't, I did say it right, I just didn't say the overestimate, underestimate part right. So, when you have error that you're willing to accept, we could say it's 5%, right? If you say smaller error, or if you agree to have a smaller chance of error, it doesn't hurt you. So if we say, I think I'm going to find a significant difference with a 5% chance of error, if you say, I think I'm going to have a significant difference with a 4.95% chance of error, that would be better than saying more, because this probability would include potentially people that are not significantly different from the population. Did I confuse anybody? I can say this again if it would help. I'm just going to say it again. So actually, I could probably draw it. That might be better. I'm going to do a new share. And let's do this. There we go. Okay. So let me draw this out. We have our normal distribution. And let's say that my red regions are alpha. In the z-score example, I was just using, I think I said that we would have a 90% level of confidence with an alpha of 0.10. So divided by 2 would mean that alpha would be 0.05 in each of these areas. Okay. So what I was trying to say with the z-score thing is it's okay to underestimate if you're using a z-table. Okay. Usually SPSS will do all of this for us, but conceptually it's kind of good to know. So we had two choices. I think it was 1. think of 1.6, not 8, 1.65 versus 1.64, I think. Let me look at my Z table really quick, just so yeah, 1.65 and 1.64. So these Z-scores were equivalent to 0.05, 0.05 and 0.0495. Okay. If we went with this 1.65, we would technically be saying that there's a little bit chance of error that we're going to be slightly further away from the mean than we meant to be. But if we're accepting significant differences when sample means or sample values land out in those regions of rejection, it's okay. Because it just means that we're saying, well, if there's a little bit less chance of error as a part of our criteria, that's fine. But if you overestimate the error and say that, oh, maybe we'll just compromise a little bit, meaning that this shaded area includes more sample values, that's not good, because then you're allowing more room for error. So hopefully that makes a little bit more sense. But that's just my example of how Z-scores translate to new share. How Z-scores translate when we're trying to get these numbers to put in our confidence interval calculations. So I've kind of put these in here for you because they are directly from the table in our PowerPoint example. But let's see what happens when we manipulate certain variables and what those variables do to our confidence interval. So hopefully everybody has this pulled up. I put our equations at the bottom so that way it's a little bit easier to keep track of everything. Okay, so I've given us a set of means and standard deviations. I've determined that our level of confidence is going to be predefined, and that level of confidence means that we have a predefined alpha, which correlates to some z-score. Okay, so all we need to fill in this equation, right, is basically the standard error, right? Because we already have the sample means, but we need to calculate the standard error. And then we've already got our z-scores. That would give us enough information to calculate the confidence interval. So if we're calculating standard error, that's standard deviation divided by the square root of n. So we can easily plug this into Excel and say equals. We do a reference to the standard deviation divided by the square root of the sample size. So plug and chug formula math like we've been doing. Okay. Show again, standard deviation divided by the square root of the sample size. So I can calculate that and then just copy it down. Right? And then I would end up being able to get the standard error for any other given mean and standard deviation. Okay. So now I'm ready to calculate my confidence interval. Okay. Remember the lower end. Oh yeah, go ahead.
So you see all that the fourth standard error is the lowest?
This one? Uh-huh.
Yeah. Would that be like the more reputable study or hypothesis?
Possibly.
Okay.
Yeah, and the reason why, because you're like, oh, well, standard deviation is 5, but the sample size is larger, right? So
you would still say that sample, though, is more closely related to its population than the other three?
It could be. And we don't really know because we don't know what the population is, but typically the smaller this standard error is, the more accurate the more accurate your estimated population mean would be.
Gotcha.
Yeah.
Thank you.
So we can use these values to calculate our lower bound of our interval, right? And again, we do minus for the lower end, plus for the upper end. So all we're doing is plugging and chugging. So we're going to do equals our sample mean minus, and then we're doing z times the standard error. So z in our case is 1.65. That's for a 90% level of confidence. Okay. Times standard error. If I press enter, that should give me the lower bound of my interval. And then I can basically do the same thing for the upper interval, but instead of minus, I do plus. So it'll be sample size, or sorry, not sample size, sample mean. Oh my God, I just realized something. Sample mean is located up here. I put the wrong number in this first one. Oh my God, I told you guys, I'm losing it. Sample mean is 60, that's a constant, my bad. But the multiplication part is still the same. So we're still gonna do z times standard error. Oops.
Would that change the standard error then?
Yes, it would. So this would, instead of C3, we would want to put 60 as well, because, no, because this one is standard deviation. So that one's fine. Those I did right. Just not the lower confidence interval, because that's including the sample mean. Okay. So since the mean is a constant, we can just put the value in. And then the upper interval would be sample mean of 60 plus z-score times standard error. Okay. So basically when we read this, I think we had this as VO2 max. Okay. Given that we have these sample characteristics, we can say with a 90% level of confidence that we would expect the population mean to exist between 58.96 and 61.04, and then our units for VO2 max. And then interval size is just going to be the difference between the upper bound of the interval and the lower bound of the interval. Okay. So similarly with these two, we could just copy them downwards, and then we're able to see how the interval changes based on certain characteristics. So we can do the same thing down in this area if we're decreasing the sample mean to 50. So we calculate our standard error the same way we did before, where it's standard deviation divided by the square root of our sample size. And then our lower confidence interval this time would be 50 because we changed the mean, minus z times standard error, right? And then our upper would just be the mean 50 plus z times the standard error, with interval size being the difference between the two. So I'm just following the formulas that are in this box. Okay, but let's see what happens to certain components when we manipulate different factors in these equations. Okay, and that's where I'm going to pull this to the next slide so we can kind of note stuff as we go. And I have the answers up here, but generally we can kind of just observe this, and I'll make this a little bit bigger. Okay, so if we're interested in seeing how the mean impacts the confidence interval, we can look at the values that we've calculated, right? So if we say 60 versus 50, right? Those are two different sample means. And we say what happens to the actual confidence interval, okay? You can note that the interval size when the mean is 60 is exactly the same as the interval sizes when the mean is 50. What's changing is the interval boundaries. So that's what I mean on the slide when we say the confidence interval shifts left to right. Remember that the mean, the population mean, is going to be estimated to be right in the center of that interval. So if we increase our sample mean, we're going to shift our interval further up in our units of measurement. If our mean is lower, it shifts down, right? So if we're looking at the sample mean shift relative to, or sample mean of 50 relative to the interval that would exist at 60, right? We can see as we increase the mean, we kind of increase the boundary. It's shifting to the right in that sense. If we change the sample size, right? So we can look at this in either one of these mean examples. But as we increase the sample size, we can notice in general, the interval size also increases. Okay, and there are some differences that we might notice, and those are kind of more or less based off of the standard deviation. But you can think about how sample size might impact confidence interval by looking at how sample size would impact our standard error. Right, so we said when we have sample size on the bottom, typically that means we have an inverse relationship with standard error. So the higher the sample size we have, the lower our standard error should be expected to be. Okay. With that, I think the best example to look at for this is these two, right? So moving from 20 to 60. And the reason why I'm choosing this example is because the level of confidence is constant. So that means the width is negative 1.96 z-scores to positive 1.96 z-scores for both cases, right? When we add more people, we decrease the standard error. If we decrease the standard error, that's proportionally related to the confidence interval. Okay, so the more people we have in our sample, the smaller our confidence interval should be size-wise. Okay, so in this scenario, sample size is a good way to kind of shift how wide or narrow your interval is, right? Obviously, the smaller your interval size is, that means the closer or more accurately estimated your population mean would be. Okay, so the narrower interval is, the more accuracy you're kind of claiming. Okay, so that's another relationship we want to highlight. And then the last relationship I wanted to highlight is the level of confidence. So now we're looking at how our intervals change based on how much confidence we have. I think this one is a little bit more intuitive, right? Because if the more and more people of your sample that you're including means the more and more people of your population that you're including, right? So if we look at how level of confidence impacts interval size, generally we see, and again, this is, these two values here are going to be different because of the sample size change. But generally we notice that as we include more people or include a higher probability that the null is going to have X number of people in it, right? Or we could say 95%, right, of our population should exist between these two boundaries. That's what the level of confidence is going to do with the interval size, is it's going to keep widening it the higher our confidence is, and it's going to narrow it the lower our confidence is. So in this relationship, as the level of confidence increases, that means the size increases or broadens, widens. If we decrease the level of confidence, we can narrow our interval. And then it's not on here, but we could also comment on standard deviation, because that's directly related to standard error, right? So if we increase sample standard deviation, that means we increase standard error. And standard error, remember, is some measure of how far away our sample mean is from our population mean. So if we're increasing that estimation error, that means the estimation of where our mean is in terms of an interval is also going to increase. Okay. So lots of different things playing roles here.
Natalie, could you repeat that last part?
Yeah. So as we increase standard deviation, or as we increase the variability of our sample, we increase the standard error.
Got it.
Which means that we're increasing the estimation or the interval size for where that population mean would exist.
Okay.
And then again, we can use this example here because we have both an increase in sample size as well as an increase in variability. But you can see that the increase in sample size has a larger effect on our confidence interval than changing the variability of our sample, right? So because our interval size is smaller with an increase in sample size, but doesn't seem to be as much affected by this increase in variability. Okay, so usually you can fix a lot of problems just by increasing your sample size. Okay, any questions on the calculations? Okay, so I'm gonna go back to sharing our PowerPoint then. And we'll do. Okay, so kind of just a wrap up of everything that we just talked about. Our level of confidence and our alpha are determined by whoever's running the test. Okay, so there are pros and cons to choosing certain types of levels of confidence. And we have examples of that when we start to talk about error, which is our next section of discussion. But usually you can say, like, I want to accept 5% chance of error, which means I'm going to have a 95% level of confidence. But you just determine that as the researcher before you run any of your statistical tests. Most of the time in our class, we're going to be using a p-value of 0.05 because that's the most commonly used one. But again, it's based on how much error you're willing to accept. Okay. And then usually it's kind of up to the reader to determine if they accept the results or not based on the level of confidence that you chose. So there's a lot of variables that you can see that go into these population mean estimations. So you kind of have to take the results with a grain of salt. If it's backed up by a lot of research, usually that's a good thing, meaning that, oh, well, my results were consistent with somebody else's. So comparability between literature is always nice. But usually it's up to the reader to say, I accept this or I don't accept this. So differences in reporting levels of confidence and probability of error. Okay. If alpha represents how much error we're willing to accept, Why is it that we say, well, if we want to be super, super precise, why can't we just say, I want 1% chance of error and I only accept results that have a 1% chance of error? Okay. Reason being is that if you look at what happens to the confidence interval, when the level of confidence increases, we said if we are including more and more of our sample, that means we're potentially excluding people who are actually different from that sample. Okay. So it's almost like giving a participation ribbon to everyone who participates. Instead of saying like, well, no, kind of you kind of suck, so bye, right? This 99% would just be like, we're including a lot more people than maybe we should. Even though it has a smaller chance of error, that could potentially be hiding significant results that might be meaningful in some way. Okay, so there's a trade-off. Right, I kind of already mentioned this, but as you increase your level of confidence, you're going to decrease your p-value, which means lower chance of error. But when that goes into our interval size, right, the more people we include, the wider our interval is, which means we have less precision on where the population mean would actually exist. The opposite is true. So if we decrease our level of confidence, that means we're going to start narrowing our interval size, because we're saying that the probability of error is higher, meaning that we're kind of excluding or including less people in the center of our distribution, and we're saying people who are at these higher probabilities in our P or alpha areas, right? We're saying that those people are potentially different than whoever's in the center. But if we're narrowing our confidence interval, we're being more precise. So then some people would say, well, why don't you just choose a 90% level of confidence if you want to be more precise? Well, then because we could be leaving out, or we could be including people who actually are the same as the population. So you see, that's why people usually use 95%, because it's semi-close to 2 standard deviations from the mean, which is where we have 95% of our population typically existing. Right? So if we can prove that somebody is in one of those 5% areas that they're different enough from that population mean, then we say, okay, well, yeah, you're different. You belong to actually a different group. Okay? So that's kind of insight to why 95 is the most commonly used one. Yes, there are pros and cons to using a 99% and a 90%, but there's also, right, you have to find some middle ground. And that typically falls on 95. So this gets us into our conversation about different types of error. And we can use this Orwellian sounding truth table. I don't know why it's called that. Probably named after somebody. But this wording has always just, I don't know. So we have different possibilities of outcomes when we run an experiment. Okay, so there are 4 different possibilities or 4 outcomes that we could potentially have. 2 of them are good things and 2 of them are bad things. You can already guess 2 are types of error. Okay, so we're gonna kind of play a game. So use your participant responses. Okay, if I accept the null hypothesis when the null is true, is that a good thing or a bad thing? If you think it's good, use the button yes. If you think it's bad or an error, use the button no.
Wait, can you repeat the question?
Yes, so we're going to look at this first square. If you think that accepting the null when the null is true is a good thing, mark it with a yes. If you think that accepting the null when the null is true is a bad thing or an error, then mark it with a no. We're We're getting more responses. It's like taking a poll. I'm seeing a lot of yeses. You guys are so smart.
How do you mark it?
Huh? What was that?
I'm saying, how do you mark it?
It's the reactions on the Zoom.
Oh yeah, the reactions on your bottom control panel.
Oh, gotcha. I was like, what?
Yeah. So this would be a good choice, right? If the null hypothesis is in fact true, we should accept it. Okay. Next question. What happens? Do same response method. So yes if you agree, no if you think it's an error. Okay. If we reject the null when the null is true, is this a good thing or a bad thing? I'm seeing X's. You are correct. And this is a type 1 error. We also call it a false positive. Okay, so type 1 error is alpha. That's the type of error we keep talking about. So this is a chance that you take when you have statistical tests, right? And you're doing experiments and you're trying to see, are groups different from each other? Are there relationships or not? The probability that you're going to make an error is referring to, oh, we might reject the null when it's actually true. In other words, we might say that there is a significant difference when there really isn't one. Okay, so that's why we call it a false positive. We think that we have a significant difference when we don't actually have one. Okay. Now we can go to this top corner. Okay, so what happens, or what do you guys think about accepting the null when the null is false? Is that a good thing or a bad thing? Okay, more X's. Okay, my other people, or my people who said that is a bad thing, that is our other type of error, which we call type 2. Type 2 error is denoted by beta, right, or Greek symbol beta. And this represents a false negative, right? So this is when we would say we don't have a difference between groups. Okay, meaning that we're accepting the null hypothesis. We're saying that the means of two groups would be equal, when in actuality they are different from each other. Okay, so accepting the null when the null is false is a type 2 error. This is related to statistical power, which falls into our last category. And statistical power is another, like one of our good decisions in this table, where we would reject the null when the null is false. So this is a positive, or a true positive, right? We have proved that there is a difference when there actually is one. And that's kind of the point of research, right? We want to show that there are significant differences based on certain types of interventions. So, or exposures, also depends on what type of research design you have, but generally in our field, we're doing experimental research, right? And we're manipulating different groups by exposing them to certain variables, okay? So power is something that we usually want to increase in our sample. And we say that it's 1 minus the chance that we'll have a type 2 error. Okay. So we can represent power as a percentage as well. And I'm going to skip to our next slide so that we can visualize this a little bit. Okay, but again, it's the probability we reject the null when the null is false. The best way to increase power is to increase sample size. And we'll have a sample size calculation example when we get to t-tests in a couple of weeks. But in that power formula, sample size is in the denominator. Sorry, sample size is in the numerator. The mean difference is in the denominator. Anyways, when we increase sample size, we increase power, okay? Because we're if we're essentially saying we're including a more representative sample of the population. If we're increasing n, we can also look at this in terms of our interval size, right? When we increased our sample size, we decreased our interval size. So increased sample size decreases interval size, right? Meaning that it's narrower. We have honed in on what the sample actually, or what the population would look like based on our sample characteristics. So if we narrow that sample size, or narrow the interval size down, right, that means that it's technically going to be easier to reject the null hypothesis because the tail area, or the region of rejection, gets larger. Okay. So that's how alpha and beta particularly are mutually exclusive, right? So if you're increasing the if you're increasing power, you directly decrease alpha, if that makes sense. Did I lose anybody? Okay. We usually want good power, right? Typically, I think power is set at like 80%. Kind of depends on the researchers, but 80% is like a good place, right? That means you're like, I'm basically 80% sure that we're going to find a significant difference. The opposite would be a 20% chance of error that we would claim that the null hypothesis is true when in actuality it's false. Okay. I have a question. Higher power. So look at it this way. If we increase power, oh, did I just say that backwards? Okay, let's go over this one more time just to make sure that I didn't screw up. So when we increase power, that means we're actually decreasing beta, right? Because the more they're mutually exclusive to each other. So if we have 80% power, we have 20% beta, right? And let me go back to this table real quick, because if you look at these two on a level here, right, the more that we increase power, the less beta becomes, and there's a trade-off between beta and alpha. So actually, as we increase power, we technically increase alpha because we're decreasing the size of the interval. However, increasing sample size also decreases the probability of a type 1 error. So I think that's why I said what I said. So typically,
So just to clarify, increasing power is going to decrease type 2 error, and then it's going to decrease the type 1 error as well then, technically?
if power is changing as a result of sample size, yes.
Yeah.
Yeah.
So it's going to cause both to decrease if it's changing due to sample size.
Technically, yes. But there's a trade-off between beta and alpha, and I have a better graphical example of this 2 lectures from now. But usually when we increase the chances of type 2 error, we're decreasing the chances of type 1 error, and vice versa. So maybe that's the better draw to make. If we increase power, we're decreasing beta. Well, no, that still gets me back to the same place. So sample size, you can increase sample size to decrease alpha and to increase power. That's what I want to say. This stuff is complicated, you guys.
In order to reject the null, you want a high or low alpha? Don't you want a low alpha?
Well, the alpha is going to be set based on the level of confidence you have. So alpha is technically not changing. Rather, it's the area of the distribution with respect to alpha. So let's say instead of what I'm trying to say is like the estimation that you have from your sample to your population. That's what we're drawing towards. So the more power you have, the more likely you're going to make an appropriate selection. Alpha itself is technically not changing because the level of confidence is set. Right? So regardless if I have an 80% power or not, alpha's technically supposed to be 0.05 if I have a 95% level of confidence. But what we're saying is that in the calculations that go into, like if we're looking at standard error, when we see how far is a sample away from a mean, those are going into the interval size, or how narrow our distribution basically gets based on our sample. I feel like I've just confused a bunch of you. I'm sorry. Just know type 2 error is bad. Type 1 error is bad. Okay. Type 1 error is the chance that you are going to reject the null when the null is true. Type 2 error is when you're going to accept the null, or accept the null when the null is actually false. Okay. We don't want either one of them. So there's certain things to consider when you have error, because a lot of how you structure your statistical analysis is going to be based on how much error you're kind of willing to accept and what type of error you're willing to accept. So you can only commit one type of error at a time. As you saw, they're on kind of different playing fields. One is when you accept the null. One is when you reject the null. One is also when the null is true. The other is when the null is false. So you can only do type 2 or type 1 error. You never know if you actually have committed an error. The only way you usually can tell is with study replication. So if you have one person who keeps replicating the same study and they consistently are getting the same results, that generally means that you probably haven't made an error. Okay. And the other thing I like to mention is that non-significant findings are also sometimes significant, right? If you're trying to prove that you have no difference between two groups, you actually want non-significant. So non-significant findings are not always insignificant, okay? Question is, on the exam, can we expect a question that asks us to create a type 1 or type 2 scenario with a given hypothesis? Usually, no. What we'll do is I'll say like, oh, alpha is 0.05. What type of error is this? And then you would identify, oh, well, alpha denotes type 1 error, so it's a type 1 error. Or I could say type 1 error is the chance that you will accept or reject. You would choose one. The null when the null is true or false, that type of thing. So I never ask you to like create scenarios, because usually we set the values of each of those types of errors when we start. But good question. Okay. So we're almost at time, and we're also almost done. So I do want to mention, I post a video with written or drawn out descriptions of when you would accept the null versus when you would reject the null, in terms of a comparison between a sample mean and a population mean. If we have extra time at the end, I might just draw it out during lecture as well, so you guys can see it twice. But if we don't get to it, I definitely would recommend watching that video. It should help connect some dots if you're feeling a little bit lost. And like I said, a lot of this is foundational material, so we will keep coming back to it and coming back to it, coming back to it, just in different types of tests, which is our next big problem, is what tests do we use? We have certain factors that we need to identify, which you guys already have practice doing. Okay, So we need to know what type of variables are being dealt with. Are they non-parametric or are they parametric, right? Categorical or quantitative. So in our class, our variables that are non-parametric are always going to be nominal. You can just write that down and say ordinal data no longer exists for this class. We use it for examples of data when we first start out, but from here on out, we're always going to have nominal, non-parametric data, okay? If we have a categorical variable. If we have a quantitative variable, in our class, it's mostly going to be ratio. There's maybe a handful of times we might look at interval data in terms of range of motion or joint angles. But more often than not, you're going to have ratio data to work with if you have a quantitative variable, something that is measured versus something that is categorized. Typically, the nominal data is going to represent groupings of people. The quantitative or ratio data will be the measurements that we actually collect on people. So that's another way you can kind of distinguish some things, right? In which case, the independent variable is usually going to be a nominal categorization of groups. The quantitative variable is typically going to be the dependent variable that we're measuring. Okay. The other thing we need to know is how many variables we have. So that's how many independent variables as well as how many dependent variables. Because the number of variables you have and what type of variable they are is going to play a role in which test you run. We also need to think about who we are measuring. Okay, we have two different study designs. There's within subjects and there's between subjects. And those are based on how you organize your sample. So we might have a bunch of different groups, say we're looking at different sports, and we categorize people into the different sports that they play. That would be a between subject design, right? Where we say we have this sample of people and we're taking a chunk of them and putting them in one sport, a chunk and putting them in another sport, and another chunk and putting them in another sport. In which case, all of our groups have different individuals. They're independent of each other, right? And we want to look at differences between subjects. Okay, that's a between subject design. If, however, we had people, say we're looking at a track event and we have like decathlon athletes who participate in the same, they all have to perform 10 events. So if we categorized certain measurements based on the event that measurement is in, and we compared different events, like the events were our groups, then that would be a within subject design or a paired samples design, where we're using the same person and we're measuring them for different groupings, essentially. Okay. And then the very last thing we have to have are assumptions. So usually, actually, every single statistical test needs to assume that there's a normal distribution. Why? Because the sample needs to be representative of the population, and the population is normally distributed. Yes, it is. Okay, so we have to meet a normal distribution. Usually you would test for normality. I think I still have you guys test for normality for the second exam. So finding z-score of skewness and z-score of kurtosis, right, are going to tell us what the distribution shape looks like. And we can figure out if we have a normal distribution or not. The other test assumption that we always want to have is a random sample. That way we're not inserting any bias into our data collected. And then usually there's going to be some type of equation that looks at the amount of variation that we have either between groups or within groups. For independent t-tests, we'll go over this later, but for independent t-tests and ANOVAs, where we have a between subject design, usually we call this homogeneity of variance. When we have paired samples, sometimes we might look at correlations between measured values, or we look at something called sphericity, which again, no definitions for those for right now, but it's basically looking at how much variance is in each sample, and is there an equal amount of variance in each sample that we can still compare the samples to each other. So that brings us to our handy dandy flowchart, which some of you are probably like, that's overwhelming. But we're gonna work through this bit by bit throughout the semester, so it won't be so overwhelming. But whenever I say, think about your decision tree, this is the decision tree, okay? So we always start with how many dependent variables there are and what type of dependent variable we have. You can see that all of the tests in this class are going to deal with the parametric dependent variable. So whenever I ask you questions on like, what type of variable is the dependent variable? That should be a freebie answer. It's always going to be parametric, which is ratio in most cases for us, or interval data, okay? We don't do non-parametric dependent variable tests over here. I used to do it, but it just seemed like a lot for the class, so I ended up taking them out a couple semesters ago. Okay, but we assess what type of dependent variable we have, and then we can assess the number and types of independent variables we have. Okay, so usually we look at, is it parametric or non-parametric? And then if it's a non-parametric independent variable, that means we have groupings or categories of people, and we're able to make levels of a sample. That's another way we often will refer to it. Okay, so then we can say, do we have one group, or do we have one variable? And then how many levels do we have of that variable? Right, so if we have two or more, there's some more complicated tests over here. If we have one independent variable with 2 levels, we then get to t-tests. If we have one independent variable with 3 or more levels, we have ANOVAs. If we have 2 independent variables, we usually have what we call multi-factor ANOVAs or factorial ANOVAs. If you introduce a covariate, that's kind of considered like a pseudo-independent variable, which is where we get ANCOVAs. Right, so all of these tests that we work with down here are going to have a parametric dependent variable with a non-parametric independent variable. The only difference is how many independent variables there are, how many levels of that variable we have, and then what type of sample. So those are big questions that I usually ask you guys for any type of scenario you have, so you just get practice picking out the important information from research scenarios, and then you can apply them to this decision tree to figure out what type of test you should run. Next week, we're going to work on regressions and correlations. Those are the only examples of where we would have a parametric dependent variable and a parametric independent variable, meaning that both values have been measured, right? And we've done scatter plot examples of correlations already. So, and I think most of you, actually all of you, have taken 312. So you have been, I know you have been exposed to correlations before because I taught the labs for that class. And Dr. Wu is a creature of habit, so I'm pretty sure he has not changed things. Okay. But these are all the tests that we're going to learn for the semester. The only things that are not on here are when we have multiple dependent variables, and that basically expands this decision tree, but instead of ANOVAs for these 4 tests, they become MANOVAs, so multiple or multivariate tests. The only exception to that is ANCOVAs, which would be MANCOVAs, which I always think sound funny. Okay, and then we kind of just could have expanded independent or paired t-tests if we have multiple dependent variables as well. Okay, so any questions so far? Okay.
So activity due next Monday?
Activity is due next Monday. And it gives you practice working on the calculations that we talked about in the lecture today. So you'll get practice. I give you like a level of confidence, and you have to figure out what the alpha level is that's paired with that. You have to figure out how to calculate confidence intervals given a certain set of sample data. And then you're also going to practice interpreting p-values in the activity. So I made this activity up last semester. It didn't used to be inserted into this part of the semester. So I actually think it helped people connect dots because I had an increased performance in exam 2, and this is where all of the foundation for exam 2 comes from. So I'm pretty sure it will be helpful in giving you practice with figuring stuff out. But yeah. So the only thing I would say, I don't think I want to do the drawing example like I mentioned. There's like the video on Beachboard. I highly recommend looking at that if the whole like do we accept or reject the null thing didn't make sense. Even if it did make sense, still watch it because it's another representation of the material in a visual format, which is honestly good for everybody. So yeah, that's it. That's all I got. That's a lot. You are welcome. I'll see you guys next week. And if you have questions, feel free to email me.